Welcome to today's Explainer. We're about to go on a seriously fascinating journey, tracing the path of digital media all the way from the creator's screen directly to the palm of your hand. I mean, think about it for a second. Just one single hour of uncompressed 4K video takes up roughly 3 terabytes of space. So, how in the world does a massive cinematic file actually fit right there in your pocket? How do we stream it so seamlessly when we're riding on a train? This is the core mystery we're going to unravel today. We're exploring how we manipulate both visuals to tell a story and the raw mathematics required to make modern media consumption even possible. Okay, let's dive right into our roadmap for today. We're going to cover 1. The art of video editing. 2. The massive data problem. 3. Lossless versus lossy compression. 4. The algorithms behind the scenes. And finally, 5. Powering modern media delivery. All right, part 1, the art of video editing shaping the narrative. Let's start right where the whole experience actually begins. You've got the modern digital workspace on one hand and traditional analog film reels on the other. At its core, video editing is just the art of manipulating and rearranging shots to create something totally new. Whether you were physically cutting strips of film back in the day or you're dragging and dropping digital clips today, the fundamentals, they're exactly the same. You absolutely have to master cutting, pacing, and rhythm to build a solid foundation for your story. And once those basics are locked in, that is when the real magic happens. Editors use advanced techniques like montage and parallel editing to literally control time and space. They layer in color grading, immersive sound design, visual effects, the whole shebang. These are the tools that grab our attention and build a really compelling emotional story. But here's the catch. Which brings us to part 2, the massive data problem behind the screen. So all of that stunning, high-resolution storytelling, it creates a massive mathematical headache. As our sources point out, an uncompressed image requires an enormous amount of data just to represent it. Now, multiply that enormous data by 24, 30, or even 60 frames every single second for video. The absolute crucial point here is this. Without the science of data compression, our phones, our hard drives, even the entire cellular network would just instantly buckle under the sheer weight of these raw files. Okay, part 3, lossless versus lossy compression, the dual solutions. To fix this giant data crisis, the digital world leans on 2 main strategies, lossless and lossy compression. Now, lossless is exactly what it sounds like. The original message is reconstructed perfectly. This is totally critical for things like text or computer code, right? Because losing even a single character breaks everything. Lossy compression, on the other hand, permanently removes unnecessary data. Why on earth would we do that? Well, because human eyes and ears are incredibly easy to trick. Dropping random, invisible pixels or high frequencies we can't even hear is totally fine for our imperfect human senses. And that is exactly why lossy is the absolute champion for media. Moving on to part 4, the algorithms behind the scenes, the math of media. So let's peek at the literal ones and zeros powering all this. Meet one of the most foundational algorithms in computer science, Huffman coding. Developed by David Huffman, this is a variable-length lossless algorithm. The logic here is just beautifully simple. Symbols or characters that pop up really frequently should take up less digital space, while the rare ones can take up a little bit more space. Think of it kind of like giving your most used contacts a 1-digit speed dial. And this brilliantly illustrates how it works. Let's take the word hello. In standard fixed-length coding, every single letter takes up the exact same amount of space. But think about how a probability tree handles it. The algorithm analyzes the word, spots that the letter L appears twice, while H, E, and O only show up once. So it groups those 2 L's together near the top of the tree. This guarantees they get the shortest possible binary code for maximum efficiency. When we look at the final math for hello, the letter L only takes up 2 bits of space, while the rarer letters take 3. When you average that out across the whole word, it is just 2 bits per symbol. That is a massive, massive space saving compared to standard uncompressed text. Just a huge win for saving data. Now let's look at a different number, 1.56. This is the compression factor you get from a totally different algorithm called Lempel-Ziv, or LZ. Instead of probability trees, LZ acts a lot more like a shorthand dictionary. It scans through a file, finds repeating phrases, and swaps them out with just a single symbol. In one of our sources tests, it took a 14-character string of repeating letters and shrank it down to just 9 characters. That gives you a 1.56 compression ratio. Now, that might sound pretty small, but it actually means you instantly wipe out over a third of the file size just by looking for patterns. So why should you care? Because these exact dictionary-based algorithms are literally the invisible engines running your digital life. Every single time you send a looping GIF meme or upload a PNG graphic with a transparent background, you are relying on the Lempel Ziv algorithm to keep those file sizes small and your internet running fast. All right, part 5, powering modern media delivery, bringing it all together. Okay, so we've got the art of video editing and we've got these genius mathematical algorithms. Let's see how they actually combine. When you look at an image online, chances are you're looking at a JPEG. JPEG is a really complex, lossy compression standard that uses a strict 6-step pipeline. First up, it converts color spaces. Then it strips out invisible color data. Next, it translates pixels into frequencies using what's called the discrete cosine transform. After that, it quantizes them to drop high-frequency noise our eyes can't even see. And finally, it uses both run-length encoding and that Huffman algorithm we just learned about to pack it all down super tightly. What's completely wild is just how efficient this pipeline really is. In just steps 1 and 2, converting the standard RGB color space into YCBCR, the algorithm essentially separates the brightness of the image from the color itself. Because our eyes are way less sensitive to exact color details compared to brightness, the algorithm just throws away some of that color data. Just from that one single step, we instantly gain a data compression ratio of 1.5, boom, done. Then we hit step 5, run length encoding. I honestly love this one because it makes so much sense. Imagine an image with a giant white sky. Instead of the computer slowly counting, pixel 1 is white, pixel 2 is white, pixel 3 is white, pixel 4 is black, RLE simply sends a quick shorthand code, 3 whites, 1 black. Because the earlier JPEG steps created big blocks of similar data, RLE sweeps in and cleans them up beautifully, saving a massive amount of space. And this basically brings our journey full circle. We've been talking a lot about still images, but what about actual video? Well, the MPEG standard essentially takes this entire complex JPEG process and applies it to moving pictures. By transforming a stream of discrete samples, mating those individual frames, into a tiny bit stream of tokens, all the heavy lifting is done. The editor's high-resolution art is finally free to flow seamlessly right through the wireless network directly onto your screen. We've seen exactly how creative choices shape our stories and how brilliant algorithms shape our data. But as our cameras keep capturing wildly higher resolutions, what happens to our media when we finally hit the absolute mathematical limits of compression? It's definitely something to chew on the next time you stream a 4K video straight to your phone. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.